everyone, Brian Beeler, and welcome to the podcast. We're here live in San Jose, California with Vast Data, and we're talking with a couple of the partners and getting their input on what Vast Data is doing, but also some of the larger industry trends. And with me today, I've got Rob Davis from NVIDIA. Rob, thanks for taking time out of your busy morning to sit with us.
My pleasure.
Should we talk DPUs or talk cars and sports?
Well, both are really fun and both are really fast. But let's stick to DPUs today.
It's funny, I did go back in the archives, I actually pulled it up. We did podcast 76 with Kevin Deerling about a little more than a year ago, talking about DPUs. And at the time,
Great.
People didn't know what it was. Like, Mellanox had been working on it, then coming in under the NVIDIA brand, and people are confused, right? It's a GPU company getting into these odd data accelerator cards, trying to figure out what's going on here. So we've done a lot of education since then. The market in 1 year has evolved so much, both in terms of what you guys have done, what competitors have done in terms of adopting these concepts. Mm-hmm. So over the last 12 months, if you can kind of summarize maybe some of the progression in the DPU world.
Sure. So we love acronyms in this industry, right? So DPU is a data processing unit.
That's a good point of clarity.
And it fits very well into NVIDIA with the GPU, because the GPU is designed to offload and accelerate compute for a CPU. A DPU is designed to offload and accelerate data movement. But a little more than that, it also does that while securing that data movement to authorized users. So
okay.
It fit very well into the whole scheme of things with GPUs and DPUs. And as you know, at NVIDIA, we're getting into the CPU market with our Grace processor in the future.
Yeah, I mean, it's so interesting because you come from a Mellanox background, so much innovation there in data transport. I'll loosely call it networking or whatever, but really it's fundamentally data getting from one node to another, from storage to compute or whatever, right? Mm-hmm. And I remember in our early days and working with Mellanox back then, it was InfiniBand in 56, and that was like unconscionable, like to think about moving that fast.
Yeah.
And then you look at that and the disruption on the switching side, and I know that there's some new things there that you guys are working on too. Fundamentally, though, a lot of things had to catch up. Software had to catch up. Operating environments had to catch up. And even the way people thought about things had to.
And the industry. So that's another component of the NVIDIA story is AI, right? GPUs in many of their applications are data-hungry beasts. They need data, more data than you can put in the machine the GPUs are in. Mm-hmm. And that's why the high-performance storage over networking has really caught up in a hurry, and DPUs have really caught up in a hurry, is because feeding those GPUs data is the lifeblood of a lot of AI applications.
Yeah, absolutely. And just as a point of clarity, I mean, GPUs stand out as like the edge cards that people chunk into gaming PCs or into servers, and that's a thing too, right?
Yes.
But when you're talking AI, you're really talking about these large graphics systems with the DGX.
Exactly. So we make a server called a DGX that has integrated into it it's sort of like a regular, think of a x86 server, but the latest one has 8 of our best, highest end GPUs built into it, and a tremendous amount of I/O slots for a lot of different things. Clustering the boxes together is one of them, but also storage. There's 2 slots dedicated, 200 gigs each, so 400 gig total, just for getting storage in and out of that box. And then we OEM a version of that, basically a motherboard that goes into our OEM partners called an HGX, which is a similar architecture, and they tend to copy a DGX design with multiple I/O slots for storage. And then there's the EGX, which are the cards you're talking about that you can put in any server. And again, those, depending on the server, you can feed just as much data into them with a technology we call GPU Direct Storage, or GDS for short, another acronym.
Well, you have to, right? I mean, it makes it easier and shorthand quicker.
There you go.
It's interesting because we were just at Supercompute in St. Louis. you've got many partners there. Supermicro was showing off their integrated design.
That's an HGX design,
which is really interesting, and others have announced them since then. It stands out to me though, and I'm sure you're not prepared for this conversation, but that as you do these things, as you put more power in these systems, that you introduce new challenges. One of them being cooling these components. I mean, you're talking about putting 8 GPUs in a box that's, Supermicro's is the one we saw is air cooled, but liquid cooling has got to be coming fast for some of these technologies.
And I got to tell you, at Mellanox we had 2,000 people. Here we have 22,000 people at NVIDIA. So there you could kind of know what was going on everywhere. I have no expertise in our liquid cooling, although I know we have it, and I know we have kits for it that we provide to customers. And
we've seen some of your partners that have new designs coming at Supercompute that we saw, and it's absolutely phenomenal what's going on there. But yeah, I mean, you talk about what DPUs are enabling, what new interfaces. PCIe Gen 5, Gen 6 was just ratified, so now that the bandwidth potential can be opened up on those slots even further.
Absolutely.
But cooling has got to be a concern for these things.
What I found in this company is there's so many smart people. I mean, Mellanox had lots and lots of smart people, but here it's on steroids, and it seems like we solve those kind of problems right and left.
Yeah, just as they come, right?
Right, as they come. And my focus is not so much worrying about the heat as worrying about getting enough data across the network into those GPUs.
All right, so let's go back to that. Organizations don't want to lose any data anymore. And by lose, I mean really get it onto old storage or cold storage. They don't want to delete anything. The industry goes through these waves, right? There was a period of time, I remember, about 7 or 8 years ago, where there was a lot of talk of deleting data. Like, you might hold on to something that could legally compromise you, so we should delete that.
I remember,
and it was more of a legal argument than a data argument. But back then, it was difficult to take a data lake and do these in-depth AI analytic workloads to mine them for anything. It was cumbersome, it was slow, it was hard. Organizations were definitely doing it, no doubt, especially in retail. I mean, they would look at trends and what does Kim Kardashian do that influences the amount of genes that we need to produce or whatever. But like there was all these data points floating around that had to be analyzed. Now nobody wants to delete anything because the more we can feed those machine learning engines, the AI algorithms, the more data, the more history, it makes a big difference, right? And you must be seeing this.
Well, the interesting thing that you learn coming into NVIDIA is more about AI, right? And what was super interesting to me was kind of an epiphany that artificial intelligence is really like people learn by experience. And what you're talking about is the data you need to feed GPUs so that they can have those lifetime experiences and form the algorithms that are the artificial intelligence. So that's why you want to keep all that data. Because if you decide, take autonomous vehicles, you see these cars driving around with cameras collecting data.
Especially out here, right?
Especially out here, or for the last 10 years out here, maybe not 10.
We don't get a lot of them in Cincinnati, but out here it's normal. Sure.
That's so that they can feed the GPU that's going to run the artificial intelligence of that car with all the things that it could see, so it gains the experience in that algorithm on how to react. And so that's why people are all of a sudden wanting to keep all this data for AI, is because you can't predict 10 years from now what kind of AI you want to implement that data could be very useful for.
Well, the autonomous driving example, I feel like, is so...
overused?
No, it's tangible, right? Because we can understand it.
Yeah.
And anyone can understand it. And that we take a car, it's got sensors all over, it's got a data collection unit in it, it's got maybe a couple SSDs in there. We've seen all sorts of implementations, but flash or whatever. But it's not really doing a lot of analysis in the car so much as gathering all this data.
It's just gathering data for those algorithms that have been not quite perfect so far.
No, exactly. But even that creates an interesting data challenge, because now you get back to the shop, you've got this cartridge or a couple drives that have, from what we've seen, anywhere from 40 to 60 terabytes of data, sometimes more. Now they've got to get
64 terabytes per day for a day of one of these collection cars is what the number that I hear from our autonomous vehicle team.
right. So now they've got to get this into a server.
Yes.
Get that data from those drives into something, right? So there's an ingest challenge.
Yep.
That can be direct attached, but eventually it gets into a big...
And if you think of a DPU that's designed to accelerate and secure storage, it's a perfect example of the little space you're trying to put this storage system into.
Mm-hmm.
Perfect example of a solution that could be done there.
And then we take the data, we keep growing our pool.
Well, then you drive the car up to the data center and plug it in at 400 gig, and boom, 64 terabytes are automatically being processed by the GPUs the same night, the day it drove.
And ideally then you get the revised algorithm, you send the car back out, and then off it goes and learn and rinse and repeat.
Because those cars also have GPUs in them to practice what the latest formula is or the latest algorithm is, and see if it's responding correctly, and keeping all the data so that when it makes a mistake, they can go back and say, oh, it made a mistake when this guy with a funny hat walked in front of it and it didn't think it was a person.
Right. We hadn't thought of sombreros on the streets or
whatever. Something like that. Yeah.
So in the old days, and even in current times, a lot of these big data pools end up being on hard drive, which is for cost metrics, or even in the cloud for perceived cost metrics, which may or may not be. We're seeing too a migration to get some of these things onto Flash, so that they're more responsive and that these models can run more quickly against large data pools. I mean, maybe talk about what you're seeing there too in terms of...
So I think you've probably, I don't think there's anything secret here that the NVMe organization has been working on hard disk interfaces for NVMe.
We've talked about that.
Yeah, so there's an acceleration point just for the hard drives to get them onto NVMe instead of, the SAS and all the controllers and complexity of that and the performance bottlenecks there. But from a flash perspective, definitely the world has gone to flash. I think the disk drives are now basically a tier, a second tier solution. And, because of you can't delete anything, tape is still there. And
we were just doing a bit on tape.
How many times have you heard tape is dead, right?
Certainly not. The density and longevity make it pretty nice to have.
And now there's this new tier of SSDs. 3D Crossbund's been around for a few years, but even the mainstream guys like Samsung with their Z NAND, right? And that is being used in applications. Actually, Fast is doing some of this where they use that as a really fast response tier, and then they have regular flash behind that. And then I think what you're going to see is a lot of the players like Vast, and I'm not saying anything I know about their roadmap, I'm just guessing because I talk to a lot of players like that, are looking at in the future adding those hard drives that are now NVMe based so they can fit right into the infrastructure as another tier. But SSDs for mass are definitely everywhere, and they've totally kicked hard drives out of the mass market.
Well, for any performance workload, obviously, right?
Yeah.
And now even more with...
I think for any market, at least is the first tier.
Right. Oh, yeah, absolutely. And I think analytics has really accelerated some of that transition, right?
Yeah,
because if you've got a couple petabytes on hard drives and you're running against that, it's
well, those DGX machines, and I don't know what Supermicro charges for them, but it's hundreds of thousands of dollars. So you're paying a lot for those GPUs. You don't want them sitting around waiting for a hard drive to load that data.
No, they can't be idle. It's just a macro version of the Creative Pro that has a $30,000 workstation with a nice GPU or two in it that you don't want that idle either.
Exactly.
And now with all this work from home or work remote or whatever the modality is for new work, the innovation that's being done in the data center to enable these high-end VDI. I just talked to Luke about this, Wignall, about he loves VDI, but so I don't want to barrage you with it, but just the concept of pulling that into the data center and getting your workloads against those things so that they're always churning.
Right.
But the same modality for for DGX, right? That thing's got to be cranking all the time.
Absolutely.
And then we talked about data transport as being part of the issue there.
Exactly, and that's where DPUs come into play as well, because they offload that data movement from the CPUs. And Kevin probably talked about this because this is one of his, I don't know, I'd call it inventions, but basically he's been talking for quite a few years now, definitely in Mellanox time, about how Moore's law is dead, right? I think our newest chip is 5 nanometer, our one after it's probably 3. Nanometers are the width of an atom, right? You have to have an insulation layer between your traces. There's an end to this. And so CPUs are not going to get any faster very soon. And so devices like DPUs that will enable the CPU to not have to worry about, I'll call them mundane tasks, like moving the data around and making sure it's secure and accelerating latency intense or latency important or CPU cycle intensive functions is super important. And that's, I think, what the world is starting to realize. And going back to like your earlier question about what's the difference in DPUs, what were called smart NICs or whatever back a couple of years ago, and where the market is now, I think that's the biggest thing, is that it's now realized as a real need going forward.
Well, I mean, if we've learned anything in our modest lab in Ohio, is that even on the latest generation silicon from AMD, Intel, configure the server however you want. Under many workloads, we can saturate those CPUs in host just with 4, 6, 8 SSDs. I mean, it doesn't take much to really stress those systems. So now what people are talking about is lanes. How do we get more lanes to the front for the drives? How do we get more lanes to the back for the I/O and connectivity? And not to diminish the value of the CPU. I mean, you need something in there to run system stuff and applications, and that's a different conversation. But getting around and offloading storage is just so natural.
Well, and with a DPU, it's designed, at least from the design input I got into the couple of generations we've had so far, to accelerate that storage. So if you think about a JBOF today, right, another one of our acronyms, right, just a bunch of flash. Today, they're like a small server. There's an x86, a bunch of memory, because x86s have lots of channels of memory, a couple of NICs, a PCI switch, and all the SSDs. And all that CPU that's designed to be general purpose to do all kinds of computational tasks, all it's doing is converting NVMe protocol coming on the PCI bus to NVMe over Fabrics protocol going out the NICs. It's a super expensive, powerful machine doing a very mundane task. And what VAST is doing, or I don't know if they're telling you this.
Yeah, we're at their thing, so we should probably talk about them eventually.
What they're doing is replacing that whole complex with a DPU. And that allows them to now build a device that's 1U, has the same or better capacity, because that technology has gotten better, of their last generation, that would be impossible if you were using an x86 architecture.
Yeah, so let's talk about that a little bit. So what they're doing, to your point, is updating their system. I mean, they're a software provider, but they work with hardware systems providers to deploy their
contract
software.
Manufacturers that they then point the customers to.
But still fundamental to that system are the pieces that go in, right? To be able to take advantage and let their software really stretch its legs.
Most of those software-defined storage guys, they spec the hardware. They say, if you want performance, here's the hardware you should buy, and here are the vendors you should go to, and it's all qualified and supported, et cetera.
And let these guys focus on the software world.
Right.
So when we're talking DPUs, yours Bluefield is take a second. Just how does Bluefield? How do you describe that? Is that interchangeable with DPU?
The NVIDIA DPU is based on an ASIC called Bluefield. That ASIC has 4 major components. The ConnectX, which is our NIC technology, I think last I looked, we had well over 50% market share in greater than 10 gigabit NICs. So that technology, which is widespread and widely accepted, is the I/O. The second component is a processor. The third component is a PCI switch. And the fourth component are accelerators. And for storage, for example, we have accelerators for NVMe over fabrics. That task of converting NVMe to NVMe over fabrics that expensive x86s are doing in JBOFs everywhere today is all in hardware. So if you look at the CPU cycles that our ARM processor is running doing that, it's like unmeasurable, less than 1%, because it's just de-encapsulating those NVMe over fabrics, NVMe commands that are inside NVMe over fabrics, and sending them right to the SSD across the PCI bus, no interaction with the CPU at all other than exceptions. So
BlueField's the silicon that goes onto the card that we would.
Yep. So all you have is that Bluefield ASIC. It's PCI switch, so it has a lot of PCI lanes coming out of it. Connect to the SSDs. Sometimes, if they need more SSDs, they'll have a PCI switch there, and then the NIC is built in, right? So inside that Bluefield is the ConnectX RTL that can go 10 to 400 gigabits, right? So basically, it's a single chip solution for a JBOF.
Yeah, and that's in the storage target in the VAST system, we would say. And then we'll get into their architecture with Jeff later, so we don't need to get too much into that.
Perfect. I'm glad to hear that, since I didn't give away any secrets.
But their architecture on the hardware side is really interesting because they're using storage class memory to front end. It could be anything behind, but I believe it's QLC these days. Behind to give really great cost metrics, but maintain the performance. Right. And now with DPU in the system, the transport is quite amazing.
And they can put it in, and hopefully he's going to tell you about this, but a 1U form factor. Right?
1U form factor. That's a big deal.
It's a huge deal, and so especially now, with the capacities.
Well, yeah, their customers now can choose to put in petabyte plus, if they want, into a single node, which is
plus look crazy. At the other aspects that go into that CPU we talked about is burning a lot of cycles that are designed to do other things, right? So it's going to use a lot more power than a DPU. It's going to have all that DRAM, which is a lot of power, because you got to have DRAM on all its channels, right, for it to work. You've got extra NICs that are generating more power, and a PCI switch. So by reducing the power, you can reduce the cooling, you can reduce the form factor, which gives you a smaller footprint, which data centers love, right? So all goodness.
Talk about complexity of networking then in a data center. What does this do in terms of my switching, my client side NICs? What needs to happen there?
You mean like software-defined networking?
Well, no, I mean physical switching. I mean, this vast thing's got to connect into switch, right?
So now you have more space for your top of rack switch, right? Obviously, is that where you're going?
Well, just what other changes occur in the data center?
Well, so VAST uses RDMA quite extensively, and most hyperscalers and even a lot of tier 2 data centers use RDMA. A lot of them don't like to talk about it, but some of them are public about it, like Microsoft Azure, for example. And they do that because a lot of their revenue comes from presenting to you with a recommender system, which is another thing that GPUs do really well. A recommender system that basically looks at what you've been doing and tries to present you with either a activity. If you're looking at race cars, it might pop up, hey, here's the Grand Prix that's going to be coming up. Yeah, exactly. Or something to buy. Anyway, it's where the revenue comes from. And so what RDMA does is give them consistent latency so that they know that before that guy is going to move to the next screen, you've popped up what he's interested in. And so they support that. And of course, the GPUs support RDMA with all kinds of RDMA offloads for congestion control and whatnot that have been learned by Mellanox, now NVIDIA, working in these very large data center environments, tens of thousands of nodes. And so that networking also applies to GPUs. So I talked earlier about a technology called GPU direct storage. What GPU direct storage does is dramatically improve the performance of getting the data from storage like VAST. And VAST supports GDS, GPU direct, the acronym for GDS, for GPU direct storage. moving the data from a vast system into the GPU because it uses RDMA, which is remote direct memory access. Direct memory access is something that's built into CPUs to move memory from one memory area to another without sitting in a software loop, load register, move, load register, move. It's just a hardware engine. You say pointer here, counter, go. RDMA does that across a network. So the VAST adapter, which happens to be an NVIDIA adapter, is told, here's a memory location, here's the counter, here's the address in the memory of this GPU, and boom, it comes across the network into that GPU memory totally directly. That's why it's called GPU direct storage. Whereas it used to go into the memory of the host CPU, which then put it in its memory. Then it told the GPU, pull this out of its memory. All kinds of interrupts in software that are totally bypassed now. Yeah. I said a lot. I'm sorry. That was a fire hose.
No, you said a lot, and then you explained it really simply. But I don't want the point to get lost because I think in the traditional data center, we think about storage as sort of a thing that just holds a bunch of our files or blocks or whatever, right? And it sits there until it's commanded to by application to do something, right?
Right.
And to get data for these AI workloads next to or into these GPUs for running the analytics, for running the models, whatever it is that's happening there. I think a lot of people think that's easy today. And maybe it's not that it's complicated, but that there is so much efficiency that's on the table.
So GDS is built into CUDA now, so it is easy.
Okay.
If you're programming in CUDA, which not everybody using NVIDIA GPUs does, you get it, it's embedded. When you say move, again, I'm not a GPU expert, but when you say move data to here, if it's remote data, it comes on GDS.
Right. Well, which is part of why what you guys are doing with VAST, I think, is so important, because VAST is building these huge scalable systems, right?
Inexpensive too, but still high performance.
Right. But most of we'll let Jeff tell us later, but most of their deployments, I think, are quite large, or can be quite large, and
definitely
many petabytes, right? And these large DGX systems, being able to get that much data into those GPU, into that funnel, through that hole to get to the GPU, absolutely, and then back out the other side.
Yeah.
The efficiency there, I think, is tremendous in terms of what it can bring, and
by using the RDMA network technology, absolutely.
And it's such a small thing, the way you just said it. So that was my point: is that you went through all these things, and then, by the way, this is how it works, and it's really simple, but not everyone's doing it that way, I guess. So I don't want to undersell what's going on.
Well,
here.
GDS is, I think we announced it. It's actually part of a bigger thing in NVIDIA called Magnum IO, and its acronym is MIO, right? But what Magnum IO is a whole bunch of technologies that accelerate I/O for GPUs. And I think we just announced that initiative and GDS as part of it at maybe the last GTC or maybe the one before it. So it's really new technology, and it's going to take a while, like anything, to get out into the installed base. But the performance difference is very, very dramatic, and I'm guessing Jeff will show you that.
Yeah, so VAST makes a relatively bold move, I think, by doing this with their software, working with their hardware partners to bring these platforms out so that customers can take advantage of this. It's not easy, right? Or everyone would be doing it.
Definitely you need to have a lot of expertise,
right.
But VAST has a lot of expertise. But there's plenty of partners doing GDS.
Right.
The big name guys are doing it too. VAST is just small and agile, and maybe not a startup anymore, but they have that attitude still that you might not find in some of the behemoths, and so they're ahead of them, right?
Well, which is fun, right? That's a good point. It's been storage disruptions. It's been a little while since we've had a big disruption. I think you've
SSDs.
Well, yeah. So you got to go back to those the hybrid arrays initially, where all these guys were coming out with, Teja. I mean, there's
remember Fusion IO and Violin, right?
Violin. That's a different story. But
No, but the PCI-based NAND that became SSDs, right? That was the disruption. But look at what it started as, just a PCI adapter with a bunch of NAND on it.
We were talking last night about Fusion IO. They at one point released a software called Ion that aggregated a bunch of these drives in essentially RAID 0, or you could do it in RAID 0. We're still running one in our lab.
No way.
It's in RAID 0. We reviewed it. I looked it up last night in 2013. Wow. We dropped the review New Year's Eve. I have no idea why we did that.
A Christmas present.
Who reads that crap at well, I don't know.
The real nerds do.
The real nerds do. And we're talking about how to share storage. Back then was, I don't even remember what the interface on that was. It might have been InfiniBand. I don't remember. But still running. And that was... Even way back then, people were trying to solve this problem.
And the hard drives were saying, oh, don't use NAND, it's going to wear out. It has wear problems, and you're still using it.
7 years later, it's been running, which is really quite remarkable. But yeah, the biggest disruptions were around flash hybrids, all flash arrays. A lot of these guys that came in to unseat the incumbents, EMC at the time, Dell, HP, before they were
Or
HP.
Seagate and WD and the hard drive side, right?
Yeah. Very
really,
much.
only one of them has made the jump,
And, so it's interesting what VAST is doing. I think the engineering bit, their hardware partners working with you guys, gives them a huge differentiation when they go to market. And we've got NABs coming up, right? There's a lot of big workloads there. GTC, which is just right around the corner, where a lot of announcements will be made around this technology.
So from the NVIDIA perspective, VAST is a super important storage partner of ours, but we have a lot of storage partners, so I don't want to make it seem like that they're the only ones we work with.
We're just at their event. So that's
okay, all right.
So we can skew.
But this is probably going to go out, and I'm going to get lots of nasty.
Oh, from your other partners?
Yes.
If you had a favorite partner,
exactly. I'm not going there. They're all my favorites.
You love all your children, but there's one that you like a little more. You could tell us about that.
Or like our earlier conversation, there's one car I like a lot more than the other cars I have.
Fast cars are good cars. So we've talked a lot about this implementation, the technology benefits that the hardware technologies, software technologies offer, VAST in this case. When you think about what you guys are doing with DPUs, what's next and what's the progression look like?
So I focus on DPUs for storage, and that's one space. I'm sure Kevin covered many other areas.
He was talking about slapping GPUs on these things as part of the potential build.
So we have a new product along what Kevin is saying. We call it had a bunch of different names. I think we called it Bluefield X or something at one time, but now
Extreme Bluefield.
Yeah, now it's called a converged accelerator. It's not even got Bluefield in the name. It's a converged accelerator, and it has our latest Ampere on it. It's available today. We're sampling it today. They'll talk a lot about it at GTC, and I don't know how much is. I'm guessing I'm okay saying this because Kevin talked about it, but it's got a Bluefield and the latest Ampere GPU, and what it's being used for a lot is what kind of is coined the name computational storage.
Right.
So there's a couple of startups that I'm going to talk about at GTC, but there's also big companies. I think Samsung has something they call smart SSD, right?
Yeah, they've got a deal with Xilinx. They're putting together these computational SSDs, but there's a lot of this. That name is somewhat frustrating because computational storage means 1,000 different things,
like DPUs or smart NICs.
you've got like scale flux that's really going after a capacity angle. You've got PlyOps, which is doing something different with a physical device and software. You've got NGD. You've got the Samsung Xilinx thing. I mean, there's a lot of them trying to figure that out.
Anyway, this card, we have startups and big customers looking at using it as a component for a JBOF. So you plug that into a JBOF. The Bluefield is taking care of all the drives like we described earlier. And what the GPU is doing is pre-sorting like pre-indexing all the data in that JBOF so that when a query comes in, you don't have to move all the data to the server so it can be indexed for searches.
Huh, okay. So it's already kind of reading ahead almost and seeing what's there. And
If you go back in time, there was these things when we were kids called IBM 360s, right? And they had IBM built something, a Shark, I think it was called, right? I think it's got some other name now, but anyway, it was called Shark, and it was their storage system. And they basically had a mainframe processor in it that did the same thing, but the thing was the size of a refrigerator.
right.
It's
Required a little more powered off.
yeah, and there's a lot more data it's
Yeah.
looking at. So, our industry, everything comes around, but that's basically what it's doing. But there's other things you can do. Think of compression, right? So different kinds of data can be compressed with more efficiency different ways.
Mm-hmm.
And so if you have a GPU that's been taught, like an autonomous vehicle, how to look at data and understand the best way to compress it, nowhere near as hard as driving a car, right?
Sure.
It could store that data in different compression algorithms into those SSDs to increase the capacity.
I mean, you talked about...
And those are just a couple examples.
Yeah, you talked about security early on, which I think is important. And
that's another thing. You can have those GPUs everywhere looking for abnormalities, in the data paths. And also, one of the great things you can do with DPUs that Modi, I'm sure, has talked to you about is you plug VMware into it. This is Product Monterey, right?
Mm-hmm.
Project Monterey that we made a big deal about it in one of the GTCs with
last year sometime.
Yeah, and basically it's a DPU that's now running VMware's hypervisor. So now the users, all the VMs are still running in the x86, but they can't get to the hypervisor. They can't get to the I/O. They can't get to the storage. It's on a different processor, only accessible through technologies that are hardware built into the DPUs. There's no software barrier to break through.
Yeah, that's pretty impressive.
And so you have this, that's why we say DPUs have security through isolation, because you can basically isolate
Right.
all the working vulnerable pieces of the security, threat, whatever they call it, threat vector, right? Away from the users. And that's kind of not my space, except when I talk about software-defined storage.
Sure.
Yeah, and in that area, it's my space.
Well, all that encryption, though, is interesting,
But that's just isolation.
No, well...
The DPUs can also encrypt data. I'm
right,
sorry.
but when you start thinking about the encryption, it really changes... it has the potential to change the value proposition for a lot of parts of the data center. Things that used to be dedupe appliances for backup targets. Now, what do we do? Because the encrypted data is not impossible maybe, but really hard to shrink it, right? Because you can't understand it and compress it once it's encrypted really well. But there's a lot of opportunity to be disruptive here to solve some of these security challenges.
Yeah, and if you've looked at, so a couple things you said there. One is encryption. It takes a lot of CPU power, even though there's special commands to do it. It takes a lot of CPU power. So that's one thing DPUs do in hardware, like the NVMe or Fabrics offload engine I talked about. There's encryption engines for all the major protocols. Our latest chip, the BlueField-2, has MACsec, IPsec, AIS, which is the AES, which is the algorithm for data at rest, the one that they do with FIPS compliance and everything. Sure. And then TLS, which is the new one for NVMe over Fabrics. All that's built in hardware engines. CPU doesn't have to do anything.
That's good.
Yeah.
Gets you all that, because that, I think we're getting to the point where some of these things are going to become standard even in the enterprise, that obviously government's been doing this stuff for forever, but
there's a new part in the government that Biden signed an executive order. I can't remember after which. I think it was when they hacked into what did they hack into? All the the oil companies or something?
Oh yeah. It was a pipeline and took
something like that.
Or
anyway,
yeah.
He signed an executive order that you not only have to now, if you're working with the government, encrypt the data at rest, but also the data in flight.
Yeah.
And so that's a big thing for storage companies that want to sell to the government. Now they can't send that data in the clear from their front end to their back end like they used to.
And so DPU helps you resolve that.
Absolutely.
I guess you could, yeah. I mean, that's maybe this one of the simpler ways to get there.
So that product we talked about that Vast will go into details on, they just turn on a switch, and now that data path from their front to their back end is all encrypted.
That should make it easier to sell into those federal accounts. And they're doing some analytics. Last I checked.
Yeah, they're probably listening to us right now.
There is no doubt about that. Well, this has been a fun conversation. I know you've got to go give your bit of talk to the group next, but really appreciate it, and can't wait to see what you've got coming at GTC here in a little bit, and
a couple weeks now,
and whatever else happens the rest of the year. With things are back, we're in person, right? It is
kind of fun,
isn't it?
It's really fun.
All right. Well, thanks for hanging out for a little bit. Appreciate it.
My pleasure. Thank you.